Hi, I'm Elliott Rouse. I'm an assistant professor at the University of Michigan and a core faculty member in Michigan's Robotics Institute. And I'm going to talk to you about a project that we've been working on in my research group, the development of an open source bionic leg. At Michigan, I direct the Neurobionics Lab. The goal of our work is to reverse engineer how the human neuromotor system regulates the mechanics of walking and use this information as a new bio-inspired blueprint for the design and control of assistive technologies like exoskeletons and robotic prostheses. Our ultimate goal is to develop technologies that get out of the lab and that impact people with disabilities. Before we begin, I'd like to tell you a little bit about how I got here. When I was younger, I worked in professional auto racing and traveled around North America and Western Europe, working on beautiful, purpose-built, $1.5 million race cars. As a young engineer, you can imagine, I thought this was it. This is what I'm going to do the rest of my life. I was a mechanic on the team. So at races, I would conduct the pit stops. So this is me, shown in blue, changing the inside tires. And we could change a set of tires in about 14 seconds. But as the years went on, I began to long for a greater impact of my work on humanity. So this passion led me to go back to school and to study the intersection between the mechanical and biomedical aspects of engineering, what ultimately became the field of bionics. So after 10 years of hard work, I run this research group. I'm very fortunate to be there and to be here. And we develop technologies to help people. And around the world, I think there are lots of people that could potentially be helped by the work that we do. But today, I'd like to tell you about one person in particular, Terry. Terry lives in Chicago. He's an artist. He has beautiful artwork around the city of Chicago. When he was a young man, he was in a motorcycle accident. So he was studying art in the Netherlands when he was in this accident, and he lost his leg above the knee. He spent many months recovering, and he was fit with a passive knee-ankle prosthesis, much like the one that you can see in this picture. Terry has excellent mobility. He's strong and fit, and he's able to use his prosthesis very well. But there are still challenges. His prosthesis is mechanically passive. So that means it can only dissipate energy or store and return energy, but it can't add any net positive mechanical energy, like what happens in the able-bodied limb when we flex our muscles. We add energy. So this makes certain activities very difficult, like going upstairs, or going up ramps, or carrying a heavy object, or walking over uneven terrain. Passive systems just cannot provide the necessary energy, and it makes him have to use his contralateral limb more. It can be more exhausting. But many people aren't as fortunate as Terry in terms of their mobility, and they have a much harder time getting around in the community. The major factor for this is the passive nature of their prostheses. This causes them to walk 40% slower on average and use about 60% more metabolic energy, so they're working much, much harder. Now, over the past 10 years or so, there's been some impressive advancements, especially in upper limb bionic limbs. We have multifunction hands and arms that can replicate many of the natural motions of the human hand. In fact, you may have seen some of this technology actually out in the public. But you haven't seen bionic legs in the public. And the reason for that is the risk associated with the control of bionic leg systems. If an upper limb prosthesis makes a mistake, he'll drop his tool, or drop his phone. But if a lower limb prosthesis makes a mistake, someone could fall down a set of stairs. So this near perfect target required for the control of lower limb prosthetics has prevented their translation out of the lab. Fortunately, we have many groups around the world studying the control of bionic legs. Here's a few examples shown on the screen. But before someone can study the development of a bionic control system, they first have to build a bionic leg, which is why each of these are different. And that's a problem for two reasons. One, it's incredibly inefficient for the field. We're spending hundreds of thousands of dollars and years to build one of these. And then it happens again and again. The second thing is, it makes comparison of the results extremely difficult. So if someone publishes results from a control system, it's very difficult to decouple those results from the hardware that they publish it on because there's no common platform. Our potential solution to this is to develop an open source bionic leg and disseminate this information to the research community. So in this talk, I'm going to tell you about the design and initial control results, and then I'll invite Dr. Levi Hargrove, who will discuss some of the higher level artificial intelligence-based control. And lastly, we'll have Terry come out and demo the full system on stage. So let's talk about the design of this open source bionic leg. We designed the system from the ground up. So it's modular, it's 2 degrees of freedom, so it's a knee and ankle that can be used either together or separately. Every decision we made to ease dissemination, ease of manufacturing, assembly, and control. We also wanted the machine to act human-like and not robotic. So that comes into the types of compliance or transmission ratio choices that we made. Robotic systems are stiff, and it's a bit unnatural for humans to work or walk with a stiff robotic prosthesis. The first choice we made was to leverage a new type of motor, a motor from the drone industry. Drones can't use transmissions. A traditional robotic system develops power with a long, skinny motor that produces a little bit of torque and goes really fast. And then we use transmissions to gear that back down to the appropriate torque speed regime. But drones can't use transmissions. So instead, the industry created the proliferation of a different type of motor geometry that's not long and skinny, but short and fat. So the drone community created this. It has more torque that lets them not use the transmissions, and they're better efficiency. So they burn off less energy into heat, which is especially good if you're carrying your power supply. But they're also difficult to control. So if you look at this motor, you'll see there's lots of different sort of coils of copper. There's lots of different magnets in there. The high numbers of poles in this makes it extremely difficult to energize the different windings in the right order, a process called commutation. So we worked with a startup called Defy to develop an efficient motor driver that's able to commutate this type of motor with a high number of pole pairs at the speeds needed for wearable robotic systems. And this open source leg uses the first driver able to do this. The application of drone motors enabled us to use low transmission ratios, but then we had to make design choices. What will it look like? For example, we searched thousands of different options. So here you're looking at range of motion on the y-axis, average transmission ratio on the x-axis, and these are for different combinations of a 4-bar linkage, which is the final stage in the ankle. And if you look, you can see, one, the type of options we chose, or we looked at, so thousands of different options, and then which one we ended up choosing. The fact that we're using a low transmission ratio also puts new options on the table. So we're able to use belt drive transmissions. So the entire system uses belt drive transmissions aside from this 4-bar linkage. Belt drive transmissions are great because they're quiet, which is really good for a bionic system. They're efficient, and they're easy to purchase. You can buy them on the Amazon of robotics. It's very different than high-performance transmissions that might take 6 months to obtain. The system is also completely self-contained, so it has onboard battery and control embedded systems for each degree of freedom. It has integrated sensing, so it has a 6-axis load cell that's built into the design, and that tells exactly how the person is interacting with the ground. We also contain 2 inertial measurement units, which are guidance chips that tell you position and orientation information. It's also how your phone switches from portrait to landscape mode. And we have information about mechanical and electrical states. So the configuration, the joint angles, the motor current, the motor voltage. And finally, we included a robotics feature in this design called a series elastic actuator. So I want to talk about that for a moment. A series elastic actuator is a mechanism type that was developed in the 90s. A traditional robotic system would have a motor coupled to a transmission that interacts with a load. That'd be your standard sort of robotic system. In a series elastic actuator, a spring is added between the output of the transmission and the load. This lets people sense the deflection of that spring as a way to learn about how much effort or force the system is providing. It's great because it improves control of effort, of torque or force. It adds safety, so now there's a compliant environment between the robot and the human. It provides shock tolerance or protection against shocks, which is good for legs if you contact the ground. And it stores and returns energy, just like our tendons in our body, also very helpful for a bionic system. But it has drawbacks. It reduces the bandwidth of the torque control or effort control, and it adds complexity and mass, which are two things you don't want for a wearable robotic system. So our field has sort of split on this. Some researchers like to use series elastic mechanisms, and some do not. So we wanted a system that was able to accommodate both schools of thought. To do that, we developed a new type of torsion spring. So here you're looking at the knee joint from the side. We developed this new type of torsion spring that consists of 24 individual radially spaced cantilever beams. And what we do is you slide a gear through the center of this, and as the gear turns with respect to the spring, it deflects each cantilever. This is helpful because it enables a really low torsional stiffness, which is difficult to obtain with springs that exist today. If you want to see me kind of interacting with it, this will give you a feel for how it works. I'm pushing on this. If you look closely, you can see the gear rotating and deflecting those springs. The stiffness of that torsional spring is about 100 Newton meters per radian. We're also able to, because of this design, stack multiple versions of these springs in parallel. So not only can the system be series elastic or rigid, you can also select the specific spring constant up to a certain value. And the way we included this in the design is helpful. It doesn't add complexity or much complexity, and it doesn't add much mass. So here you're looking at a cutaway of the knee prosthesis. You can see the belt drive transmission stages. And if we look at the knee joint, so this is the last stage of the belt drive system, and that large outer pulley, that's the knee joint axis. Inside that, you can stack up to 6 of these different springs. So this gives researchers options, and hopefully it also encourages them to use it for their control. Now I'd like to tell you a little bit about how bionic legs are controlled. The lowest level of control, low-level control, runs at about 1,000 hertz, and it's closing local feedback loops. So this is reference tracking. It's tracking a position change or a current change. So this is the lowest level of control. A mid-level control, this operates at about 200 hertz, and it contains information, a model about how the system should respond for a specific activity. So it knows at this point, it knows what's going on. Let's say a person is walking, and it has some sort of mathematical relationship that it implements and passes reference trajectories to the low-level control. And finally, the high-level control is an artificial intelligence-based controller that's identifying what someone is doing. Someone's walking or standing or going upstairs. That's running at about 5 hertz. So I will share with you results about low and mid-level control, and Dr. Hargrove will talk about high-level control. So low-level control, one potential reference might be tracking a position signal. So the way that we can quantify how well a system tracks a position is by using a step response test. So here you're looking at the knee and the ankle trying to track a change in position. So up to about 15 degrees. And you can see it looks like it tracks pretty well. Another version of characterization of control would be not how well does it track a step signal, but how well does it track a signal with multiple frequencies. So we call this a bandwidth test, where the knee and ankle are shaking around as hard as they can. And these are pretty fun tests to conduct. So we can quantify how well the system tracks different frequencies, and that information is typically shown using something called a Bode plot. So the takeaway for its position control tracking is its rise time is about 26 milliseconds. That's about how long it takes to reach its target. That's a little bit slower than it would take you to blink your eyes. The overshoot is about 2.4%, which is low. That steady state error, less than 1%. and the bandwidth is about 10 to 20 hertz. And that's about 3 times better than the human neuromotor system. We also have quantified the system's ability to track a torque signal or an effort signal. And instead of talking about that in terms of the time domain and frequency domain characteristics, like we talked about for position control, I'll show you the results of a rather intuitive test. So this is a bona fide robotics test where you interact with the system, and it's tracking a reference of 0 torque. So it's supposed to reject everything that the torque associated with its own inertia, the torque associated with friction, and the fact that it can do that without breaking its Ritz cracker means that it has pretty high fidelity torque control. Now I'd like to tell you about mid-level control. Hopefully I've shown that we have some sort of high performance, low-level control. And mid-level control, as I mentioned, uses information about a specific activity. So this already has encoded in it knowledge of what's happening. Someone is walking, for example. A common mid-level controller is to represent the system as a time-varying stiffness, virtual damping parameter, and virtual equilibrium position. And these values can be changed depending on how you want the system to respond. This concept is known as impedance control. And if you change these parameters carefully or with a specific order, you can add or remove exact amounts of energy. To give you an example of what that looks like, here's the knee again, programmed to operate in impedance control mode. So what you're seeing is it's acting like a spring. So you can see it oscillates. So that's sort of a spring-like behavior. You can see that there's damping because the oscillations die out. And then you can see that it changes position on its own. And that's changing this equilibrium position or this rest length of the virtual spring element. So now I've demonstrated to you that some of the design, some of the low and mid-level control. And at this point, I'd like to introduce Dr. Levi Hargrove. And he will talk to you about some of the work his group has been doing in terms of control of the bionic leg.
So thank you, Dr. Rouse. I'm really happy to be here to share some of the work that our group has been doing. I'm from the place called the Shirley Ryan Ability Lab, which used to be known as the Rehabilitation Institute of Chicago. And we've spent several years developing intent recognition systems for bionic arms and legs. And similar to Elliott, I'm trained as an electrical engineer, is my background. But I also really had a passion for helping people. And so this is, I'm not in a fancy fire suit, but that is in fact me, working with Amanda Kitts and developing some of the preliminary bionic arm control strategies at the Rehabilitation Institute of Chicago. And so we've been working in this area, the field has been since the 1940s, and the devices have been used clinically since around the 1970s. The most sophisticated systems in use today use statistical pattern recognition. And the way that they do that is they decode the neural information from your muscle signals. So these signals are called EMG, myoelectric signals. Each time a muscle contracts, it generates a little tiny bit of electricity. It's about 1/1000th of a AA battery. It's very small. But with sensors on the limb, you can detect these signals quite reliably, amplify them, and then send them to an algorithm for decoding. And so we can decode movements at the wrist, we can decode finger movements. It really just depends on the sophistication of the decoding algorithm. This video is a bit dated, maybe 5 years old, but it illustrates the process of using this in real time to decode a virtual limb in this case. So the name of the game is you kind of have these very random looking EMG signals that are detected, amplified, and we use a real-time embedded system to transform the EMG signals from a random state into a highly structured, generally a feature space. And we use simple statistics like the amplitude or frequency content of those signals over a short time window to make that transformation. After they've been transformed into a feature space, you can use any number of machine learning algorithms to partition that space. We support vector machines, mixture models, neural networks, deep networks, Name your favorite classifier, and someone in this myoelectric control industry has probably tried it with some degree of success. And these aren't just in the laboratory anymore. These are, in fact, available to patients around the world. So these are examples of real upper limb amputees using bionic arms. A number of very nice hands, hooks are available. This has been on the market for the last 5 or 6 years, fit to hundreds, if not thousands, of amputee users now. So they take these devices home, incorporate them into their daily environment, but they're not perfect. They do make mistakes periodically. The hand might not close in the gesture that you had selected. So we had thought when we started this work on bionic legs around 10 years ago that we would just apply these experiences that we had developed directly. We would use statistical pattern recognition to decode knee and ankle joints. And it kind of worked. So this is an example. The guy's name is Zach Votter. He's had a surgical intervention to restore some ankle control information. But generally, we're using the same tried and true algorithms that we had developed for controlling arms to control the knee and ankle. So he's able to mimic the movements of the therapist. He thinks about bending his knee, flicking his ankle, what have you, and the device kind of responds in real time. You can see he can time the contractions, so I'll kick a soccer ball to him and he'll be able to time the contraction to do some kind of a semi-functional activity. Now, he's of course not using this to stand up at this point or to reposition it for a transition, but it shows that we have the building blocks in place. Unfortunately, walking is different than just sitting in your chair, repositioning for comfort. It has to be highly accurate, and the best systems that we have just simply cannot do this in real time, continuously at the knee and ankle to decode all of the movements. So that brings us back to the control strategy that Elliott, that Dr. Rouse introduced earlier, and he went over the low-level control, the mid-level control, but I really want to focus on the high-level control and how that kind of interacts with the mid-level control. So generally, we use finite state-based control systems, and we generally break gait into 2 main phases and then some sub-phases within that. So we usually have stance. That's when your weight is on your leg or your prosthetic limb in this situation, and it needs to behave generally stiff to hold you up. And the other phase is swing. And so this is kind of a compliant state where your leg might be swinging around. It's not bearing your weight. And to transition between stance and swing, we can use sensors in the device, like a load cell. How much weight do you have on the device? If it's not very much, you're in swing. If it's a lot of weight, you're in stance. So this is a pretty straightforward way to control something. And we can make more complicated state machines for cyclic activities. So we typically try to use 4 states in our control system. We have early stance, so that's when you have weight acceptance, and late stance, which is kind of a push-off. And early swing, that's when your knee is flexing, and late swing is when your knee is extending. So for walking, a cyclic activity, we can again use mechanical cues, like when do you have weight on the device, when do you not have weight on the device, what's your tibial angle, which we measure through an IMU, to transition between early and mid stance. It's pretty easy and straightforward to develop these transitions. We can restore different activities. So we have stair ascent, we have stair descent. Where possible, we try to keep it in this 4-phase activity, just for keeps things straight in our mind, and it's pretty effective. And just to point out, I have a couple of equations on the screen. These are just, in fact, the impedance control law that Dr. Rouse mentioned earlier. So these are essentially how we generate the joint torques using an impedance control model. So each one of the boxes are a set of tuned spring damper systems that generate the required torque. So we hand tune these based on experience. You can also hand tune them based on, or guess them based on a model, but they generally require some hand tuning in the end. So transitions around a cyclic activity are pretty straightforward. Transitions between different types of activities are really difficult. It's hard to know in real time when you want to transition between activities. And we, in fact, use machine learning to figure out all of the transitions between all of the activities in a safe and robust way. So this is a cartoon of a control system. We have software that we've developed, and we call it CAPS, control algorithms for prosthetic systems. We use it for controlling both arms and legs. And this is an example of what our software might look like, and you'll probably see this later on during the demo, and showing all of the within state transitions. So these are no transition between states, and these are the states that are generally informed using AI. And so these are the transitions that happen between any different states. It looks very complicated. I just want to point out that a lot of these transitions are for edge cases for safety. So we always have to have a safe and reliable device. And so while it looks pretty complicated, it's actually not too bad. And we, of course, hide all of that complication from end users using a simple phone app. So you can see our little mobile phone. The user generally wants to know if they're walking or transitioning between activities, not what state in transition 372 looks like. So we hide that, make it very simple and easy for people to use. So the name of the game is predict the next step. We're always trying to predict the next step. If you're walking, what are you going to do? Or you want to go up a stair? Do you want to go down a stair? Do you want to stand? Do you want to pivot? Do you want to turn? And if you don't get the transition right, bad things can happen. It maybe is not functional, or it's maybe a safety critical situation. So in this situation at the bottom of the step, if it didn't transition, it would kick the stair and you'd be unable to climb the stair. But because it did transition, his trajectories change, he can ambulate. If it doesn't transition back to walking, it's potentially going to hold the leg up in the air and not be in a position to bear his weight. So those are kind of key points in the gait cycle where we actually have to have very reliable. If it didn't transition here, he would jackknife over the leg because it was too stiff and fall down the stairs, potentially. If it didn't transition here, it would be too compliant and it would feel like he's walking in a hole. Similarly, going on to ramps, a little bit less of a critical transition. I'll talk about that in a minute. But it also allows him to have a more natural gait going up and down ramps. And finally, one last transition from walking down ramps. This is, in fact, the hardest one to learn. Very difficult to get that first step on the ramp. To predict the difference between that and walking is very challenging. And then back to walking. So those are kind of what we're focusing on to start with, and also standing, which I haven't shown in here, but we also allow standing and shuffling. So we have a number of different sensors that we can measure from. So we have load cells. We have information from the state of the joint, so position, velocity, acceleration information from the knee and ankle. We have inertial sensors. And we also have EMG signals or muscle signals from legs as well. And if you look at the different activities, you can see different shapes in the sensors. So for example, the knee, which is the knee sensor, which is the second one down in the third column, it looks very different from the second one down in the second column. So we visually can see that, and it's pretty straightforward to teach any sort of algorithm how to classify that. And so that's in fact what we do. Because we don't always have EMG signals available, we kind of use a sensor fusion-based approach. So we take an estimate of the class or movement based on EMG. If it's available, we take an estimate of the class of motion based on mechanical sensors. You can add in computer vision, which we have, in fact, done on several occasions. So you can kind of pick your experts and fuse them using a kind of a naive Bayes approach or another method. There are many approaches that work. The key is that it needs to be in real time and respond to within 10 milliseconds of the user intent. That's kind of the key. And so we don't simply do straight line. We do cuts and pivots and turns. You can tell that the AI system is in charge here because we have therapists for safety. These are highly experimental devices. The less showy it looks, the better for us because this is meant to be someone's leg. But it is, it's a cool robot. The guy's walking around doing different activities, local control, responding in real time, processing probably 25 sensors in this example. And this is, in fact, Terry, who you'll have a chance to meet later, testing one of the earlier prototypes maybe a couple years ago. Again, transition down the step, nice and compliant. Figure eights, kind of wandering, lots of different activities that you have to restore for users. It's not always correct. We make mistakes. I stub my toe when I walk. That's maybe my control system. That's maybe my laziness. I'm not sure. The control system does make mistakes. Sometimes the impedance control parameters, the spring constants, they're so similar that the patient doesn't notice it. If there's a misclassification between ramp ascent at a shallow incline and walking, the spring tuning parameters are so similar you don't notice it. Oftentimes it feels like I stubbed my toe or I'm walking in a hole. So it's a little bit too compliant, but it doesn't cause the person to fall. If you were to ask them what it feels like, it's like, I feel a little bit unstable. I don't like that. I'm not sure I would want to use this every day, but I don't think I'd fall. Kind of jackknifed over the top because it didn't get the prediction at the right time. Again, that's the trickiest one to get in our experience. If it doesn't transition at the bottom, it feels like he's walking in a hole. He kind of went down on it. These are things that can go wrong if we're not accurate. This is a dangerous one. So he's walking down the step and it makes a mistake and it wasn't ready to bear his weight. So without the safety harness and without the therapist spotting there, he could have fallen and injured himself. And so, during these, I'll call them still kind of early to mid stages of our research, we still have to have lots of safety mechanisms in place because things can go wrong. Now, an opportunity that we have when controlling legs that we don't have when controlling arms is that we can use real-time learning. So we can learn as the person walks. We can detect mistakes and make corrections because we know what normal gait should look like. And so to get into a little more of the nuts and bolts of how we do this, kind of what we do, we're continuously measuring signals. We're always measuring them in real time, and we're looking for events. So when does the person load the device? When do we have an onset of force in the vertical axis on the load cell? We detect that event, and we look back in time just a little bit at all of the sensors that are in a buffer, and we extract features. So we extract features, and we make a prediction. So basically, we say, in our feature space, this looks in this location. Our best estimate, based on the probability, is in this case, ramp descent. What's generated by the user depends on that prediction. So if it does not predict the parameters for ramp descent, it's going to behave differently. So we compare these generated profiles to what would be normal from a textbook or from our experience with clean data. Nope, wasn't that one. Nope, wasn't that one. We made a mistake. We made a mistake. This is what you actually did. So our prediction algorithm made a mistake. We know that from a second expert, which is much easier to identify what you did after it happens than predicting what you're going to do next. And we adapt our control system. We do that every step. So make an estimate, check what you did. We have some thresholds on probabilities to make sure we do it in a nice, safe way. But that's generally the idea on how this works. So with that, I'd like to bring it back to Terry. So as Dr. Rouse mentioned, he's an artist. This is his studio. He's been working with us for several years, and I want to bring it back so that we can get ready for the kind of the fun part of the show, which is introducing you to Terry.
So in just a moment, we'll invite Terry on stage, and he'll begin by answering a question about how his bionic leg compares. During the time when Terry is walking around with the bionic leg, data will be shown on the screens. So on the right, you can see the state machine that Dr. Hargrove talked about. As he's walking, you'll see the classifier changing locomotion activity and changing states within that activity. It'll also be displaying data real time on the left. This is one of the first on-stage demos where people use a bionic leg with multiple activities. And I say that not to impress you, but to give you an idea for how serious this demo is. So this is a very challenging feat. As a result, Terry will be accompanied by therapists as he's walking around. And then after the demo, we'll have a brief conclusion and then go to question and answers. So at this time, we'd like to bring Terry on stage. So as he's walking around, you can see that the motion of the leg is very natural. And as Dr. Hargrove mentioned, you can hear the classifier is continually making a decision about what he's trying to do, and it understands that he's walking right now. As he approaches the stairs, you'll see it transition on its own automatically, which is exactly what it's supposed to do. And if it were his take-home prosthesis, he would not be able to go up step over step. He'd have to shuffle step to step. So here it's about to transition into stair ascent. And he'll come onto the stage. Welcome, Terry.
Thanks, Elliott.
So could you take a moment and just talk a little bit about how this bionic leg compares to your passive take-home system?
First of all, I want to say what a joy it's been working with Elliott and Levi over the last 7 years, be among the first people to walk on this cutting-edge technology, especially coming from old world technology. But to address your question, Elliott, I'd like to use the analogy of the two legs as the difference between a girlfriend and a lover. I mean, a girlfriend, you have to coddle, you have to make sure everything is right, you have to carry around everywhere, where a lover, you're intimately involved, you're connected, your thoughts are the same. That's what this leg is like. It's a treasure and a joy, and it has the potential to make my life a lot easier.
Great, so now Terry's going to exit the stage, walk around, and we'll talk you through some of the data that's being shown on the screen. So it's going to transition automatically to stair ascent and transition back to level ground walking. So if you look on the left, you'll see data streaming from the device. It's being telemetered from the onboard embedded system to the laptop, which is showing the data. The pink signal is the vertical ground reaction force, or the amount of weight that he's bearing on the leg. The green signal is the angle of the knee joint. And the red signal shows the angle of the ankle joint. So the classifier is kind of continually looking at these signals, breaking them into features, and then detecting activity mode. So Terry's going to come up on stage. We're going to pause here. We're going to transition back to the presentation. We'll have a brief conclusion, and then we'll answer questions. And you're welcome to ask Terry any questions that you might have about the bionic leg. So our goal was to change the lives of individuals with disabilities. And the approach that we took was to develop an open source platform to really spur on the controls development, which is one of the most challenging parts. I'm excited to say that up to right now, 6 other groups around the world are either using it or about to be using this bionic leg to test their control strategies. And this presentation also marks the public release of the website where you can download all the information about this bionic leg. It's opensourceleg.com. This is an example of the landing page. There's a bill of materials. There's all the solid model files. There's information, detailed step-by-step information about how to assemble the system and how to control it. And there's a forum for people to say what they like and don't like, or what design changes they want, or upload their own changes. So I hope to really foster this concept of this open source dissemination. We would like to thank the National Science Foundation and the MSL Renewed Hope Foundation who sponsored this development. We'd like to thank Terry for his continued effort and input on this project. We'd also like to thank our teams for making this research possible. So it took 7 people. It's an interdisciplinary team of student scientists, clinicians, prosthetists, therapists to make this demo happen. And we also look forward to future advancements that are enabled by this technology. Thank you.